In this video, we discussed Simpson's rule, which is a numerical integration technique. In the last video, we discussed the trapezoidal rule. So with the trapezoidal rule, what we did was we created a line segment from point to point on our graph here. First, let's say we're trying to approximate the area from A to B under the graph of f of x between the x-axis from x equals a to x equals b. We said we could have done that with those rectangles like we did in the past, or we could approximate with trapezoids. If we're approximating with trapezoids, basically what we're doing is we're approximating the function itself with a linear function. So we would create a linear function from one point in the partition to the next point in the partition, the next point and the next point and the next point, and so on. We create a partition where all of the subintervals have equal width. And then we would create a trapezoid, or if the function value happens to be 0 on either endpoint, it's just a triangle. And then basically we approximated the area under the curve with the area of these trapezoids. We said, well, let's just take the area of this triangle and this area of this triangle and add the area of this trapezoid and the area of this trapezoid. And we ended up with this formula in terms of these function values for a function that gave us an approximation of the area under the curve. But again, we were just coming up with that linear approximation of the function on each interval, and that led to this trapezoid rule. With Simpson's rule, rather than using a linear function, we use a quadratic polynomial. So we'll have a polynomial of the form ax squared plus bx plus c for each of these intervals. And rather than just using 2 points and approximating the curve with a quadratic polynomial, we're going to use 3 points. With 3 points, that will allow us to determine the values of a, b, and c, and we'll be able to graph the function there. And then, and we'll do that for every two intervals, so that we're using 3 points at a time. We'll use these 3 points for the first polynomial, and then these 3 points for the second polynomial if our interval is from, say, 0 to pi, and our number of subintervals is 4, just for instance. But basically, we're going to do that pairwise with Simpson's rule. Okay, so before we can approximate the function using a quadratic polynomial and then taking the area under the curve of each of those quadratic polynomials, we need a theorem. This just says that if p is a second degree polynomial, so it has this form, then the definite integral is exactly equal to this. Now this is just b minus a divided by 6. So it's the length of the subinterval divided by 6. And then we have 3 function values. We've got the value of the polynomial at one endpoint, plus the value at the polynomial at the other endpoint. And then we've got 4 times the value of the polynomial at the midpoint between x equals a and x equals b. That's why we're using this formula. We're coming up with this formula here, and then we're going to apply that to points on the curve. If we use our even or our regular partition, so that every subinterval has the same length, this would be the polynomial at the first point. This is the polynomial at the last point, and that's our polynomial at the midpoint. So our polynomial will always pass through those 3 points on the curve itself. So it'll be an excellent approximation to the function itself. Yeah. So let's prove this. It's actually just a lot of algebra, really. So we've got the integral from a to b of our quadratic polynomial. And we can evaluate that using the fundamental theorem. This is really just algebraic manipulation more than anything else. So we add 1, a is a constant, then we add 1 to the exponent and divide by the new exponent. And then b is a constant. For the x to the first, we add 1 to the exponent and divide by the new exponent. And then the antiderivative of the constant c is just x. Then we evaluate this from x equals a to x equals b. Substituting b, we get 1/3 capital A times b cubed plus 1/2 capital B times b squared plus c times b. And then we evaluate this at that lower limit of integration, lowercase a. You're just replacing the x with an a. And then we'll distribute the negative through the parentheses. That negative gets distributed there and there and there. And then we look at this form, notice that we've got a b minus a out front. So what I'm looking for is to factor this. I need to be able to factor out that b minus a divided by 6. And then I want to see that function evaluated at a. So I want to see this quadratic expression, but instead of having an x everywhere, instead of an x squared and an x, I'm going to have an a squared and an a. And for the polynomial at b, instead of an x squared and an x, I want to have a b squared and a b. And then we're probably gonna have to do a little bit more algebra for that expression at the midpoint, but we should be able to figure it out. First of all, I notice that I've got that b minus a out front and the 6 in the denominator. So I think what I'll do is I will group the terms that look a little bit similar. I've got this 1/3 a b cubed and the negative 1/3 a times lowercase a cubed. Factor out the 1/3 capital A, and then we'll have b cubed minus a cubed. Then these two terms are similar. I'll factor out the 1/2 capital B, and then I've got a b squared minus, I think I wrote, shouldn't that be squared? Yeah, that should be a squared. B squared minus a squared. And then these two terms look similar. I've got a CB minus CA. So if I factor out the C, we got C times B minus A. Now a difference of cubes factors. That's going to be B minus A times B squared plus AB plus A squared. A difference of squares factors, that's B minus A times B plus A. And then we've got C times B minus A. Now, when we look at all of these, and I look at this and this and this, I see that they all have that B minus A in common. And I know I want that 6 in the denominator. So I'm going to factor out a 1/6 times B minus A. And then I say to myself, okay, I need this to be a 1/3. If I take 2 times 1/6, that would be 1/3. And I'm trying to say, I also say to myself, well, 1/6 times B minus A. If I take 1/6 times B minus A and I multiply it by what do I have to multiply by, excuse me, so that I get this first term here? Well, to get the 1/6, I needed 2. To get the capital A, I needed a capital A. And I've already factored out the B minus A. So what I'm left with is that B squared minus or plus AB plus A squared. And then here I say I factored out that B minus A. I need this factor of 1/2. In order to get a 1/2, I need a 3 because 3 times 1/6 is 1/2. We need a capital B. And 3B times 1/6 is that 1/2 B. The B minus A is accounted for, and then we're still left with that B plus A. And then over here, I need a 1C, and I've factored out a 1/6, so I need an extra factor of 6. 6 times that 1/6 gives us a 1, multiplying the C. And then we've already factored out the B minus A. Okay, so that's what we have. And again, we're looking for the polynomial evaluated at A and the polynomial evaluated at B. So if I distribute, this is what I get. Got 2A B squared plus 2 capital A AB plus 2 capital A squared plus 3B B plus 3 times capital B times lowercase a plus 6C. And the claim is there is a polynomial evaluated at A there. So I need an A times lowercase a squared plus B times lowercase a plus C. Okay, let's see, where are those terms? I had a 2 times A times 2 times capital A times A squared, and I took one of those for my polynomial evaluated at A. So I'm still gonna have an extra one. No, that term is accounted for. Where's my BA term? Well, I had 3 of them, and I took one of them for my polynomial at A. So I need an extra 2B at times A. And then for the c, I had a 6c, so I'm gonna make that a 5c. And then we've got these other terms as well. So we've got plus 2a b squared plus 2a times little ab plus 3 times capital B times lowercase b. It's just a bunch of algebra, really. But this is my polynomial at a. Okay. Now I also need my polynomial at b. So I need capital A times lowercase b squared plus capital B times lowercase b plus c. And I'm taking that from these terms. So I need a capital A times b squared. I've got 2 of them. So there's going to be another one left outside the parentheses. Then capital B times b, I've got 3 of those. So I'm going to have 2 of those over here. And then I took one of the c's, so I've got a 4c left outside. And then I've got some additional terms. I've got capital A times a squared plus 2b times lowercase a plus 2a times ab. So this is my polynomial at b. Supposedly this is 4 times the polynomial at that average value of a and b. See, I don't know if I see it. Well, there's a bunch of terms involving capital A. So I've got an a times b squared, an a times lowercase a squared, plus a 2a times ab. If I factor out the a from that, I'm going to have a squared plus from this term 2ab plus b squared. Hopefully you recognize that as the quantity a plus b squared. And then here I've got a 2b times lowercase b plus a 2b times lowercase a. If I factor out the 2b, I've got an a plus b there. And we have a 4c. So I'm starting to see something that looks like that polynomial evaluated at the midpoint. Like capital A times a plus b quantity squared plus b times 2 times the quantity a plus b plus 4c. I think that might be exactly the polynomial evaluated at a plus or at the average value of that a and b and then multiplied by 4. To see that, I think I'll just calculate what that is and see if it matches. Might be easier that way. So P evaluated at that average X value is going to be A times A plus B divided by 2, quantity squared, plus B times A plus B divided by 2, plus C, square the numerator, square the denominator, and then multiplying by a fraction is the same as multiplying by the numerator and then dividing by the denominator. And we'll multiply this entire thing by 4. When we distribute the 4, we get A times the quantity A plus B squared. And this 4 times the 2 will leave us with a 2 in the numerator because 4 divided by 2 is 2. And so we get exactly what we have right here. So this is actually 4 times P at that average X value, or that midpoint of the interval from A to B. Now this derivation is a little bit boring, I'm not gonna lie. I don't really think it's that exciting myself. It's just a lot of algebra. But the result I think is kind of cool, because what the result says is as long as we have a second degree polynomial, whenever I integrate from A to B, if I want to find the value of that integral, all I really need are 3 function values. I need to know the function value at the left endpoint, the right endpoint, and at the midpoint of that interval. If I know those three function values, I know the exact value of that area under the curve. I don't even have to know the coefficients A, B, and C. For any coefficients A, B, and C, and for any lowercase a and for any lowercase b, this is equal to this. And I think that that's pretty cool. I've got some pictures online. I just like to graph these things that just demonstrate that that's true for different choices of capital A, capital B, and capital C, and lowercase a and b. But what's nice about it, again, is that you can find the exact value of that area under the curve with three function values. And if you know what the polynomial is, it's very easy to find three function values. Just plug in the points, simplify, and you've got three answers. Just substitute them in, and then you'll know what this is, which I think is pretty cool. So let's look at that. So here's our polynomial, ax squared plus bx plus c, with our coefficients a equals 3, b equals 5, and c equals 6. Just got a quadratic polynomial. It's just a parabola when you graph it. Nothing fancy. If we're on the interval from -2 to 3, a is -2, b is 3, and the point halfway in between is 0.5. We can see the function values here. P at b is 8, P at a is 8, P at b is 48, and that middle function value is 9.25. If we evaluate the integral from a to b, we get 77.5. That's the area under the curve. If we evaluate this sum on the, we get 77.5. So this 8 plus the 48 plus 4 times this 9.25 times the length of the interval, which is 5 divided by 6, is the exact value of the integral. And what's cool is I can change b and see they're the same. I can change a and they're still the same. I can even change the coefficients of the polynomial, so I make the polynomial have different shapes. And even so, guess what? They're still the same. It does not matter. Whoops, I don't know how to get out of there. Like, I zoomed way in. I don't know what happened. Let me refresh that page. Save it first. I accidentally zoomed way in. I don't know how I did that. But the point is, regardless of what A, B, and C are, these two values are always the same every time. No matter what the bounds are, and no matter what the coefficients of that polynomial are. All right. Now that allows us to develop Simpson's rule as well, because that will allow us to compute the approximate area under the curve for a particular function using a second-degree polynomial as an approximation. Now for Simpson's rule, we say, okay, this is what we're going to do. We want to subdivide our interval into n subintervals of equal width. That's delta x equals b minus a over n. And we're going to require n be even. So we want an even number of subintervals. Now, if n is even, we'll be able to group the subintervals in pairs. So we start at a, which what we're calling x naught, and we have x naught, x sub 1, x sub 2, x sub 3, and those are increasing. So x sub 1 is greater than x naught, x sub 2 is greater than x1, and so on. Eventually we get to x sub n minus 2 and x sub n minus 1. And finally, x sub n, which is b. And then we're going to group the, looks like 2 intervals at a time, but it's really 3 x values at a time. That's how I tend to think of it. I'm going to group these 3 together. So from x naught to x sub 2. And focus on that interval and come up with a polynomial to approximate the function. And then we'll do x sub 2 to x sub 4 would be the next one. And then x sub 4 to x sub 6 and so on. And the last one will be x sub n minus 2 to x sub n. That's why we require that n to be even so that we can do that. Okay, and then on every one of these subintervals, we'll approximate f by a polynomial p. So it'll be from x sub I minus 2 to x sub I. The integral from x sub I minus 2 to x sub I of f of x is approximately equal to the integral from x sub I minus 2 to x sub I of our polynomial. Our polynomial approximating the function. And then according to this rule that we just came up with, this is giving us the definite integral of that polynomial on that interval. So we know the exact value of that area under the curve, or that net area under the curve for a polynomial if we know 3 values on the polynomial. Well, if we approximate f by a polynomial, a second degree polynomial using 3 points, we're going to have a polynomial that passes through all of those 3 points. And we'll talk about that in a bit. But we know the exact value of this. It is x sub I minus x sub I minus 2 divided by 6 times p at that first x value plus 4 times p at that midpoint value, that midpoint between the 2 x's, plus the final, the p at the final x value of that interval. And this x sub I minus x sub I minus 2 is related to delta x. Delta x is the length of the interval from x naught to x1. So if I'm going from here to here and then here to here, the length of that interval is 2 times delta x. The subscripts make it look worse than it actually is. Now 2 goes into 6 3 times, and delta x is also b minus a over n for the larger interval. So we end up with b minus a over n times 1/3, so b minus a over 3n times this for each subinterval. Now because every, how do I say this? Since we know that the polynomial, we're going to require our polynomial to pass through 3 points. The 3 points on the original curve for f of x. Since we require that polynomial to pass through the 3 points, these function values for the polynomial are equal to the function values for the original function. So this is going to be b minus a divided by 3n times the function value at x minus, or x sub I minus 2 plus 4 times the function value at that average x value on the interval plus the function value at the endpoint of that interval. Okay, so if we look at the graph now, Here's x0, x1, x2, and so on. We're going to find a quadratic polynomial that passes through those 3 points. And this is going to give us the exact area under the curve for that polynomial. And that's going to be a very, very good fit most of the time. This is that exact area. But if we are doing that for the interval from 0 to 2, or from x0 to x sub 2, excuse me, and then on the interval from x sub 2 to x sub 4, we're going to have this expression. Let's just use 4 subintervals, for example. We'd have this for that first sort of ordered triple, where we've got those first 3 points, and then we would do the same thing for the next 3 points. But you see what happens is the one that we started with at the beginning, we only use that function value once. But this one we're going to use twice because we use it as the endpoint of this for this interval, and then we use it as the starting point for the next interval. And if we do that for a number of intervals, then we end up with Simpson's rule. So here's Simpson's rule. It says let f be continuous on the closed interval from a to b, and let n be an even integer. Then the integral from a to b of f of x is approximately equal to that b minus a divided by 3n times the function value at x0. And then we're going to use this approximation for the, so you get a polynomial approximation for those first 3 points there. We'll have f at x0 plus 4 times f at x1 plus f at x2, right? And then for the next interval, we can factor out that b minus a over 3n. We'll have f at x2. And I've got another, I've already have one of those from the previous interval, so I have 2 of those. Plus 4 times f at x3 plus f at x4. And then if there's another interval after that, this will be the end point of the last interval, and then it'll be the beginning point of the next one. So I'll have a 2 times that, and we'll keep going. And then the last one will be a 4 times f of x sub n minus 1. And then the last one will just be an x sub n. So what I want you to notice is the coefficients go like this. We've got 1, 4, 2, 4, 2, 4, and it's going to keep going. And the last ones are going to be 2, 4, 1. We only use the first value, or we only use f at x0 once. We use f at x sub n once. That's actually f of a and f of b, if we prefer. But then all of these other ones, this with the even subscript, so for x sub 2, x sub 4, x sub 6, and so on, as long as we're not at the very end, we're going to count all of those twice, because we're using that for one interval and then for the next interval as well. So this tells us how to approximate the function with that second degree polynomial, and it's actually a really excellent approximation. So that's our rule. And it turns out that as n goes to infinity, this approximation approaches the actual area or the actual value of the integral. So I'm going to write the right-hand side approaches the value of the integral. Okay. And then we've got some error estimates for this. But I think what I want to do is actually apply Simpson's rule for a particular function. I'll show you how to find those polynomials that approximate the function. But one thing I do want you to notice is that we could use this Simpson's rule to approximate the area under the curve using polynomials without actually knowing the polynomials. We're going to find the polynomials so that we can visualize it for one particular example, but you don't even have to know what the polynomials are to know what that approximation of the appropriate best fit polynomial would be, or for the area under this function, which is actually the exact area under that quadratic function that would fit through those 3 points on the interval from, say, x naught to x of 2 or x of 2 to x of 4. And so we're going to revisit that example that we looked at using the trapezoidal rule. We've got the integral from 0 to pi of sine of x. We want that area under the curve. And we want to use 4 subintervals. We're only using 4 because it makes our calculations a little bit easier. So if delta x is b minus a over n, that's going to be pi minus 0 divided by 4, or pi over 4. And so half of that interval is pi over 2. Then we'll take half of that to get 1 pi over 4, and then this is 3 pi over 4. And the function values that we're interested in are these. We got f of x equals sine of x. So we'll evaluate sine at 0, at pi over 4, at pi over 2, at 3 pi over 4, and pi. We've done all of this before. At 0, we get sine of 0, which is 0. At pi over 4, we get sine of pi over 4, which is square root of 2 over 2. At pi over 2, we get sine of pi over 2. That means we're at the top there. We get a y value of 1. At 3 pi over 4, the y value is the same as the y value at pi over 4. So we get the square root of 2 over 2. And then at pi, we get 0. Okay. So if we want to now, we could use Simpson's rule. This is approximately equal to, what was it, b minus a divided by 3n, was that correct? I lost my formula. Going to be b minus a divided by 3 times n, and n is 4, times the function value at 0, plus 4 times the function value at 1, plus the function value at 2. And that's going to be our approximation on this interval. And then we're going to add the function value at 2, plus 4 times the function value at 3, plus, or not 3. This should be x sub 0, x sub 1, x sub 2, x sub 3. And then the final one is f at x sub 4. All right. And then x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4 are these values right here. So we end up with pi divided by 12 times 0 plus 4 times square root of 2 over 2, which is 2 root 2. And we've got 2 times 1, which is 2, plus 4 times square root of 2 over 2 again, which is square root of 2 over 2, plus 0. And our approximation of that area is, well, this is 4 times the square root of 2 plus 2 times pi over 12. Everything is divisible by 2, so I'll factor out a 2. And the 2's reduce. So we get 2 root 2 plus 1 times pi divided by 6. I don't know what that is approximately, but that's an approximation of that area. And if we wanted the exact value of the area, we could always just use the fundamental theorem of calculus. Now, we tend to use Simpson's rule when we can't use the fundamental theorem, but I like to, whenever I use a numerical method, I like to get the exact answer when possible so that I have something to compare to. If I was using the fundamental theorem, I just take the antiderivative of sine of x, which gives me negative cosine of x, substitute in x, substitute in pi, and subtract. So we'll get negative cosine of pi minus a negative cosine of 0. Subtracting a negative is the same as adding. This is a negative 1 times negative 1. So we get positive 1 there, plus 1. 1 plus 1 is 2. So this is 2, and that is our approximation. So let's look at Desmos and see what that is approximately. And then let's try to come up with those polynomials that approximate the function on those intervals. So here's our function. And I've evaluated the function at all of those, that x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4, just like before. Now, in order to find the polynomial that passes through these 3 points, well, actually, let's do all the numerical stuff first. Let's do the Simpson's rule part. This was the value that we came up with when we did the calculations by hand. It was 2.0046 approximately. And then when I had Desmos calculate that for me, they also gave me the same decimal approximation. So I know my hand calculations and Desmos's calculations are the same. And we can see that the difference between the actual integral value, which is 2, and this is less than 0.005. So it's very, very small error. You might say, okay, how can I find a polynomial, a quadratic polynomial that fits through those points? Well, one thing that we could do is we could plot those 3 points. I just typed in the x values, and then I had Desmos calculate the corresponding y values. We could also do that by hand. 0, square root of 2 over 2, and 1, right? And then I used the regression capabilities of Desmos to find the coefficients of that polynomial. So I said f of x sub 1, where x sub 1 are the x values in this column. I want that to be given by a quadratic polynomial. I used ax squared plus bx plus c, but rather than using x values, I just used x sub 1. And it found the coefficients for me. I can also find those coefficients by solving a system of equations. And it turns out that these are what the coefficients are. My a value is 8 times the quantity 1 minus the square root of 2 divided by pi squared. Just want to copy and paste that. You see it's that negative 0.3357. It's the same as the value that they're getting when they use the regression capabilities of Desmos. And then my b value was 4 times the square root of 2 minus 2 divided by pi. And that is the same as the value calculated by Desmos. So we can use Desmos's coefficients, and that's going to give us the right polynomial. But I actually solved a system of 3 equations and 3 unknowns, and we're going to do that in just a second so we can find that polynomial. But when we do, we graph it, this is what it looks like. If you zoom in a little bit, you can see that polynomial is the orange line and the sine curve is that teal line. It's very, very close. You can see that's an excellent approximation to the function. So if I were to shade that region, the area under the orange line, can't you imagine that's going to be very, very close to the area under the teal line? I think it is. And it turns out that we get the exact value of that area when we use that formula that we derived using all of that algebraic manipulation. F at 0 plus 4 times f at pi over 4 plus f at pi over 2 times that b minus a divided by 3n. That actually gives us this exact area, and it's really, really close to the area under the curve for the original function. And we're actually using the original function values because we required our polynomial to pass through those points. You can do the same thing on the second subinterval. I just typed in the second set of x values, pi over 2, 3 pi over 4, and pi. Then I had Desmos calculate the coefficients. I had to use some different labels. Rather than a, b, and c for the coefficients, I used a sub 2, b sub 2, and c sub 2. Just to have different labels because it was already using a, b, and c for the last polynomial. I calculated these coefficients by hand as well by solving systems of 3 equations and 3 unknowns. And it turns out that my coefficients are equal, if I look at the decimal approximations of my coefficients, they're equal to the decimal approximations of a, b, and c calculated by Desmos. So that is actually an excellent approximation. Or Desmos actually calculates those coefficients for us if we want to. If we don't want to do the algebra necessary to find the coefficients ourselves. But there's our polynomial. Look at what a great fit that is. Very, very similar to the original function. So now if I look at the area under that polynomial, which is exactly that b minus a divided by 3n times this function, times the sum of this function value 4 times this function value plus 1 times that function value, we get the exact area under that orange curve. And so we're using this orange area as an approximation under the curve of the original function. And we see that it's an excellent approximation. When we look at the approximations, we get 2.0046, which is only slightly larger than the actual area under the curve, which is pretty cool. So that's how we use Simpson's rule to approximate the area under the curve. Computing that area is relatively simple to do. You just use the formula. We know where it comes from because we derived that formula for the integral from a to b of a second degree polynomial. And we can see visually that using that second degree polynomial as an approximation to the function is an excellent thing to do. It's a good approximation, an excellent approximation of the original function, much better than the linear approximations that we were using before. Okay, so if you're saying, I really want to know how to find that polynomial, I'll show you how to find the polynomial just for the first one. It's relatively simple to do. And then once we find that polynomial, we'll compare it to the answer that I got last time I did it. And then we'll do the same thing for a second example. But I don't think we'll go through the rigmarole of finding the coefficients of the polynomial every time, because if we did that for a lot of intervals, it would take a very long time, especially if we don't have a calculator that can do linear algebra. So let's do some of that calculation by hand on paper. Okay, so we want to find the polynomial that fits through these 3 points to approximate the curve y equals sine of x on the interval from 0 to pi over 2. So I'm going to use these 3 function values. So I want my polynomial to satisfy these, or have the same function values as my original function at 0, pi over 4, and pi over 2. So to find those coefficients of a, b, and c, all right, let's let our p of x be ax squared plus bx plus c. Then at x equals 0, I'll call this p sub 1 for the first subinterval, or for that first like sort of double subinterval, right? Because it's doing that delta x plus delta x for those first 3 points. If I evaluate at 0, this is what I get. So I just get c, and f of 0 is 0 because we're talking about that sine function, right? I'm going to require this to be 0. So this just tells me that c equals 0. So the only non-zero coefficients are a and b. Then at pi over 4, our function value was square root of 2 over 2, or approximately 0.707. I said pi over 2, I meant pi over 4. So a times pi over 4 squared plus b times pi over 4 plus c, which is 0, has to equal square root of 2 over 2. So if I simplify that, I've got a times pi squared divided by 16 plus b times pi divided by 4 equals square root of 2 over 2. Now, if we want to clear those fractions, and I do want to clear the fractions, we can multiply by 16, multiply every term in the equation by 16, and then we'll have 16's reduced there, a times pi squared plus the 4 is reduced there, 4b times pi equals, well, the 2 reduces there, 8 times the square root of 2. That's one equation involving a and b. A and b are unknown, and we're trying to find those coefficients. Now we also want to require our polynomial to have a value of 1 at pi over 2, because we know that when x is pi over 2, the sine function is equal to 1. So we want a times pi over 2 squared plus b times pi over 2 plus our c, which is 0, to equal 1. And if we simplify, we get a times pi squared over 4 plus b times pi divided by 2 equals 1. And to clear the fractions, I might multiply everything by 4. Then the 4's reduce. The 2's 2 goes into 4 twice. We end up with a pi squared plus 2b times pi equals 4. So we've got 2 equations and 2 unknowns. If I solve those 2 equations and 2 unknowns for a and b, then I'll know my polynomial on that first and for those first 2 intervals. So I've got a pi squared plus 4b times pi equals 8 times the square root of 2, and a pi squared plus 2b times pi equals 4. We can subtract those. Then we'll have 2b times pi equals 8 square root of 2 minus 4. We'll divide both sides by 2 pi. We have b equals, if we factor out of 2, we get 2 times 4 root 2 gives me that first term. 2 times negative 2 gives me my second number. Divide by the 2's, and we get that as our coefficient b. And then since we know what b is, we can use this equation to find a. A pi squared is equal to 8 square roots of 2 minus 4b pi, or 4 times pi times b. The pi's reduce. And then we will distribute that negative 4. We've got 8 minus 8 root 2. And then divided by pi squared is our a. So the first polynomial, the polynomial on that those first 2 intervals is given by a divided by pi squared times x squared plus b, which is 4 root 2 minus 2 divided by pi times x, plus c, which happens to be 0. So this is my first function. And I will use this on the interval from 0 to pi over 2. And I'm writing it like that because that's how we type it into desmos.com. See if it's the same polynomial that I came up with before. Yeah, 8 times, or 8 minus 8 root 2 divided by pi squared is my a, and then 4 root 2 minus 2 over pi is my b. If that's my P1. That's what it was.
Yeah, the guy.
That's what the graph looks like. Now I'm not going to solve the system of equations for P2, but I'll show you how to set that up as well. So P2 is just another quadratic polynomial, and we want it to pass through these 3 points now. So we want it to have the same function value at pi over 2, 3 pi over 4, and pi as our original function, which happened to be sine of x. So at pi over 2, sine of x is 1. At 3 pi over 4, sine of x is square root of 2 over 2. And at pi, sine of x is 0. We want our polynomial to have those values as well. If we substitute those values for x, we end up with 3 equations and 3 unknowns. So I'm going to have a times pi over 2 quantity squared plus b times pi over 2 plus c equals 1. And if we simplify, we've got pi squared times a divided by 4 plus pi times b divided by 2 plus c equals 1. I don't like those fractions. I'm going to clear them by multiplying everything by 4. And 4 divided by 4 is 1. 4 divided by 2 is 2. So we end up with pi squared a plus 2 pi b plus 4c equals 4. That's our first equation for our system of equations. That's one equation with 3 unknowns, a, b, and c. If we evaluate at 3 pi over 4, got a times 3 pi over 4 quantity squared plus b times 3 pi over 4 plus c equals the function value at pi over 4. The original function was sine of x, so that was square root of 2 over 2. If you simplify, you have 9 pi squared times a divided by 4 squared, which is 16, plus 3 pi times b divided by 4, plus c times, or equals, square root of 2 over 2. Multiply by 16 here, and here, and here, and here. To simplify, 16 divided by 16 is 1, 16 divided by 4 is 4, 16 divided by 2 is 8. So we have 9 pi squared a plus 12 pi b plus 16c equals 8 times the square root of 2. So that's our second equation. And then for our third equation, we evaluate at pi. We have a times pi squared plus b times pi plus c equals the sine of pi, which is 0. That's our third equation. We've got 3 equations and 3 unknowns. Pi squared a plus 2 pi b plus 4c equals 4. Oops, I can't see that. Now with 3 equations and 3 unknowns, usually we just choose a variable that we want to eliminate. We say, which variable do I want to get rid of? Trying to take 3 equations and 3 unknowns down to 2 equations and 2 unknowns. Then you want to take 2 equations and 2 unknowns down to 1 equation and 1 unknown. You solve that equation. Once you have that value, you back substitute to find the value from, or the variable from the second system of equations. And once you have your first 2 values, you substitute those 2 values into one of the original equations to find the third. So it's really simple. It requires a lot of work, and it's not necessary for this problem. But I just wanted you to see that it is possible to find that a, b, and c so that the polynomial has the same function values as the original function. And that's what we choose. That's what we always find. It's a little bit tedious, but it's relatively easy to do. I'm not sure if we should do it. I don't know. We haven't solved the system of 3 equations and 3 unknowns in this class, so let's do it. I want to get rid of the a's first. So I'll call this equation 1, this equation 2, and this equation 3. So in order to get rid of the a's, I see that pi squared a for both of these. So I think I'll take equation 1 and subtract equation 3 in order to get rid of the a's. When we subtract them, these guys are gone, and we just end up with pi times b plus 3c equals 4. And then you might say, okay, I'm trying to get rid of, I've already used the first equation 1 and equation 3. So now I need to use equation 2, and it has that 9 pi squared in it. So I'll take equation 2, and I'll subtract 9 times equation 3. And so I'll just write down my equation 2. And then if I multiply this by -9, I've got -9 pi squared a minus 9 pi b minus 9c equals 0 times -9, which is 0. These guys are gone. We get 3b pi there. And then 7c equals 8 times the square root of 2. Okay, so now we took our 3 equations with 3 unknowns, and we are down to 2 equations with 2 unknowns. I've got a pi b and a 3 pi b. So to get rid of this, to get rid of one of the variables, I'll choose to get rid of the b's, because if I multiply this equation by -3 and add them together, then the b's will be gone. So I'm going to call this equation 1 star and this equation 2 star. I'm going to take equation 2 star 3b plus 7c equals 8 times the square root of 2, and I will subtract 3 times equation 1 star. So we'll have negative 3 pi b minus negative 3 times 3c is negative 9c, and negative 3 times 4 is negative 12. So we'll get negative 2c equals 8 root 2 minus 12. And if we divide both sides by negative 2, we can change the order. I'll make that 12 minus 8 root 2 divided by 2. 12 divided by 2 is 6. 8 divided by 2 is 4. So I get 6 minus 4 root 2. So that's my c value. Now that I know c, I can use one of these equations from earlier to find b. And once I know b, I can use one of the equations from the beginning to find a. So we know that pi b plus 3c equals 4. So b is equal to 4 minus 3c divided by pi. And c was 6 minus 4 root 2. Distribute the negative 3. Of negative 18 there, and negative 3 times negative 4 is positive 12. So that's my b value. I'm wondering if I made some errors already. All right, so there's our b, and we have our c, and we know that a times pi squared plus b times pi plus c equals 0. So a is equal to negative b times pi minus c divided by pi squared. So if I multiply this by pi, or by negative pi, this is my b value, I should get 14 minus 12 root 2. And we're subtracting c, and we're dividing by pi squared. Distribute the negative. 14 minus 6 is 8. Negative 12 root 2 plus 4 root 2 is negative 8 root 2. And we're dividing by pi squared. And say, okay, what were we doing again? We're trying to find that polynomial that fits through the points. Our polynomial was a, which is that value, times x squared, plus b times x plus c. But only on that interval that we were interested in. This was on the interval from x equals pi over 2 to x equals pi. Hopefully we did those calculations correctly, but I just wanted to show you how you can do it and how requiring our polynomial to pass through these 3 points defines that quadratic polynomial. It leads to 3 equations and 3 unknowns, a, b, and c. And so we will be able to find a polynomial that fits through those points. And that's the polynomial that we find on paper is the same polynomial that Desmos finds when it uses the regression capabilities. So it is the same polynomial I calculated earlier and typed in. So we're saying that is the approximation of the function. And we're saying the area under the curve there, plus that area under the curve. That's given by that exact formula that we derived earlier. It's very, very close to the area under the, between the sine function and the x-axis on the interval from 0 to pi. Now there is an error estimate theorem in the section covering this material in the text. It says, if f has a continuous fourth derivative on the interval from a to b, then the error in approximating the definite integral using Simpson's rule is less than the following maximum value. It doesn't tell us where the error maximum comes from, but it says take b minus a, raise it to the fifth, divide by 180 times the number of subintervals, raised to the fourth power, and then multiply by the maximum value of the absolute value of the fourth derivative on the interval of interest. Well, we're talking about the sine of x. If we take the derivative 4 times, we're going to get sine of x back, right? First derivative is cosine, second derivative is negative sine, third derivative is negative cosine, and then the fourth derivative is we're back to sine of x. So the maximum value of the sine function is just going to be 1, and our maximum error is just this b minus a to the fifth, which in our case, for this particular example, is pi minus 0 to the fifth. Then we divide by 180 times the number of subintervals. And we chose 4 subintervals. So this is going to be 4 raised to the fourth. So this tells us that our error is going to be less than this 0.00664 approximately. Now, if we look at the exact error, so we had this approximation of the area using Simpson's rule is 2.0046 approximately. And we know that the exact value of the integral is 2. And we could evaluate the integral from 0 to pi of sine of x. We're going to take that and subtract the approximate area that we calculated using Simpson's rule. And we see our actual error was 0.0046, and the maximum error was 0.0066. So our actual error was less than the maximum error. This just gives us an interval. It tells us like how it tells us what n essentially would need to be, like how many subintervals we would need to have to get an approximation to a certain accuracy. So if we wanted this error to be even smaller, rather than using n equals 4, we could use n equals 6 or n equals 10. We could use more subintervals, and then we get an even better approximation. Let's see what it would be if n equals 10. Then our error would be less than 0.00017. I don't want to do all the calculations to compute those polynomials on those intervals. If n equaled 10, we would have what, 1, 2, 3, 4, 5 polynomials that we would have to compute in order to graph it and illustrate it. But we could still find the approximation of the area with n equals 10 relatively simply, just splitting this interval from 0 to pi into 10 subintervals. So I'd have 0, pi over 10, 2 pi over 10, 3 pi over 10, and so on. Those would be my function values, and then I would use that coefficient pattern that we talked about. Let's actually do it for n equals 10. So I'll use pi over 10 here, then I'll use 2 pi over 10. And I know we could simplify that, but just to make it more obvious, I'll just use 3 pi over 10. Then we'll do 4 pi over 10. And the coefficients switch from 4 to 2 on the interior, plus 4 times f of 5 pi over 10, plus 2 times f of 6 pi over 10, plus 4 times f of 7 pi over 10. You can see it's kind of tedious, but really we're just following the pattern. 8 pi over 10. There's a way to write this, code it, that would be much simpler. I just don't know how to do that personally. And then the last function value we only use once, right? So f at pi. Because my approximation is 5 now. That's not right. I think I've got the wrong n at the beginning. Yep, I should have 3 times n in the denominator, so that's 3 times 10. And so there's my approximate area now. We look at the difference between the actual area and the approximate area with n equals 10. We've got an error that's actually 0.000109.5-ish. and the error, the maximum error was 0.00017. So we were able to make that error smaller by taking that step size, or excuse me, the number of subintervals to be larger. And we can make that error as small as we want, essentially, by taking our n large enough. So this formula can be used to allow us to infer the number of subintervals that we should use to get the approximation of the integral to within a desired accuracy. For this particular integral, we could just use the fundamental theorem and we get the exact value. But in other problems, you might not actually be able to find the value without a calculator or without a numerical method like this. So you might just decide, I want to find the value of the integral to this accuracy. How many subintervals do I need to have? Then you could let this error max be less than the error that you want, and then just solve for n essentially. And that would tell you how many subintervals you need to use to get that value. Now, I don't want to graph that because it would be a pain, but I hope you understand that we would just subdivide this into 10 subintervals of equal width. And then we would have 5 different polynomials that pass through like each set of 3 points. So I think that's it. We could do this again for another example. I think I might do another example in a different video, but that's Simpson's rule. You don't have to calculate the polynomials in order to use Simpson's rule. But if you do calculate the polynomials, it can be done relatively easily by solving systems of equations, 3 equations and 3 unknowns. And then you can graph them and you can visualize it and you can see what a good approximation it is to use the polynomials to approximate the area under the curve. Second degree polynomial rather than the linear polynomial that we use at the trapezoidal rule.